In the last few lectures, we had examined the flow around a particle and the flow around a bubble. Okay. We saw that for the flow around a particle, there are multiple flow patterns depending upon the Reynolds number for the particle relative to the fluid based upon the free stream velocity. Okay. And we had examined correlations in each of these regimes and also tried to see what is the range, the variation of the drag force with Reynolds number, okay. The variation of the drag force with the Reynolds number. Okay, in each of these regimes. Okay. And we had also looked at different types of correlations for low Reynolds numbers, for intermediate Reynolds numbers, and for high Reynolds numbers, and looked at an example of the particle diameters and masses for which these different types of correlations are observed. Okay. And we had also looked at the flow around a bubble. Okay. The difference is that in the case of a gas bubble, there is relative fluid velocity relative to the surface is non-zero, whereas for a particle it is 0 in general, okay, because of the no slip condition. And because of that, the correlations have a different form in the case of flow past a bubble, as we had seen. Okay. And we had also looked at the regimes for which the Reynolds number and the capillary number are small and large. Okay. So, here we will next consider what is called a packed column. Okay. A packed column is a column of particles through which fluid flows through. Okay. In the previous example, we had considered a single particle moving relative to the fluid. The results we derived there can also be used when the volume fraction of particles is small, so that the flow around one particle does not affect the force exerted on another particle. Okay. The packed column is the opposite limit, okay, where basically you have a very large number of particles. Okay. And fluid is being pumped through this column, okay, by an external pressure difference that is applied across the particles. Okay. The particles are in contact with each other, so the stability, mechanical stability is maintained by the interparticle contacts basically. Okay. And then fluid flows through the voids between these particles. Okay. The bed diameter I will call it as d, and the particle diameter I will call it as dp, or d equivalent diameter for a single particle. Okay. So, if I look closely at a particular location within the packed bed, okay, I have particles with voids in between them, and the fluid is basically flowing through these voids. Okay. The fluid is basically flowing through these voids. Okay. And the equivalent diameter of the particle is what I will call dE. Okay. So, that is the equivalent diameter of the particle, and the fluid velocity is given by what is called the superficial velocity Vs. Vs is the velocity which is basically the flow rate divided by the cross sectional area of the bed. Okay. It is not the cross sectional area of the voids between the particles. The superficial velocity is defined as the flow rate divided by the cross sectional area of the bed. Basically, the velocity that the fluid would have if there were no particles. Okay. So, it is the cross sectional area of the entire packed column, okay, without particles in it. The relevant velocity for us is actually the velocity with which the fluid flows through in between the particles, okay, which is much higher because the particles occupy a large fraction of the space, and therefore, the velocity with which the particle fluid flows through the particles is higher. Okay. And these packed columns are important in many situations, because they can increase contact between the fluid and the particles. Okay. You have a very large surface area of contact between the fluid and the particles. Okay. And the important parameters here are the superficial velocity and what is called the void fraction. Okay. Which is basically the fraction of the packed column that does not have particles. Okay. So, it is basically 1 minus the volume fraction of particles. The volume fraction of particles could vary anywhere between about 0.6, 0.64 for spherical particles to as low as 0.2 if you have odd shaped particles. Okay. If you can make odd shaped particles in such a way that the void fraction is the fraction of volume occupied by particles is small, and therefore, the void fraction is large. Okay. So, the parameters here, okay, are the superficial velocity, okay, the velocity, the flow rate divided by the cross sectional area of the packed column, okay, the void fraction, which I will denote using this epsilon symbol, okay, the void fraction, and the diameter of the particles. Okay, dE is equal to equivalent diameter of the particles. For the transport processes that happen as the fluid flows through the voids between the particles, the relevant length scales are not the particle diameter, but rather the equivalent diameter of the void between the particles. Okay. So, basically we have to calculate the length scale as the equivalent diameter of the voids between the particles. Okay. We know that the equivalent diameter of voids, okay, okay, is going to be equal to 6 times the volume of the voids divided by the surface area of the voids. Okay. Volume of the voids divided by surface area of the voids is the hydraulic diameter, okay, for in 3 dimensions, okay, and 6 times the hydraulic radius. Okay. So, hydraulic radius is equal to V of voids by the surface area of voids. Okay. And 6 times the hydraulic radius is the equivalent diameter. Okay. And that is the length scale that we have to use in our definitions of the Reynolds number, the friction factor, etc. Okay. So, what is the relevant length scale here is the equivalent diameter of the voids or the characteristic dimension of the voids. Okay. So, how do we calculate that? Okay. What is the volume of the voids? Okay. So, I will denote Vp as the particle volume and Sp as the particle surface area. Okay. And V as the total volume of the packed column. Okay. And N as the number of particles. Okay, N is the number of particles. So, what is the void fraction? Okay. So, the void fraction, okay, the volume occupied by particles is N times Vp. Okay. N times Vp is the volume that is occupied by particles. Okay. That is divided by the total volume is equal to the fraction of the volume that is occupied by particles, the volume fraction occupied by particles. The void volume fraction is 1 minus the volume fraction occupied by particles. This is equal to the void volume fraction. Okay. Volume occupied by particles divided by total volume is the particle volume fraction. 1 minus that is the void volume fraction. Okay. And this can give us a relationship for the number of particles n. Okay. So, therefore, the number of particles n has got to be equal to V into 1 minus epsilon by Vp. Okay, that is the number of particles. Okay. So, we had defined the void fraction, the equivalent diameter for the voids, okay, as d void is equal to 6 times the void volume fraction by the surface area of the voids. Okay. The surface area of the voids is the same as the surface area of the particles. Okay. The surface area of the voids is the same as the surface area of the particles. Okay. The surface area of the voids, because at the interface between a void and a particle, on one side is the particle, the other side is the void. Okay. So, the surface area of the voids is the same as the surface area of the particle. Surface area of void is the same as the surface area of the particles, which is n times the particle surface area of one particle. Okay. So, I should note here this is Vp and Sp that I have been using is one particle volume and Sp is one particle surface area, okay, one particle. Okay. So, S void is equal to n times Sp, okay, and this I can write it here as V into 1 minus epsilon, okay, substituting for n, Sp by Vp. Okay. That is the surface area of the voids, okay, and the surface and the volume of the voids is just equal to epsilon times V. Okay, that is the void fraction. Okay. Therefore, the equivalent diameter of the voids, the equivalent diameter of the voids is equal to 6 V void by S, sorry, yeah, okay, which is equal to 6 epsilon V by, okay, V into 1 minus epsilon into Sp by Vp. Okay. Just substituting the surface area of the voids in here. Okay. And you can easily see that this is equal to 6 epsilon Vp by 1 minus epsilon Sp. Okay. Okay, just substituting for the surface area of the voids and the volume of the voids, the total volume V cancels out in both cases. Okay. Now, this factor of 6 Vp by Sp is the equivalent diameter of okay, 6 Vp by Sp is the equivalent diameter of the particle. Okay. So, this is going to be equal to equivalent diameter of the particle times epsilon by 1 minus epsilon. Okay. Okay. So, therefore, the actual length scale for the void, okay, d void equivalent is equal to 6 epsilon equivalent diameter of the particle by 1 minus epsilon. Okay. Okay, is equal to the equivalent diameter of the particle into epsilon divided by 1 minus epsilon. So, that is the length scale for the flow through the voids. Okay. That is the length scale for the flow through the voids. Okay. And the velocity scale for the flow through the voids, okay, V voids. Okay. This will be equal to Vs divided by epsilon. Okay. Because the volume of voids divided by total volume is equal to epsilon, right, and therefore, the velocity of the fluid through the voids, okay, will be equal to the surface superficial velocity Vs divided by epsilon, okay, because that is the velocity with which the fluid has to flow through the voids. So, that the flow rate, okay, is equal to Vs into the cross sectional area of the bed, okay, because the void cross sectional area is equal to epsilon times the cross sectional area of the bed. Okay, the void cross sectional area, okay, the cross sectional area of voids is equal to epsilon times the cross sectional area of bed. Where epsilon is the void fraction, okay, and because of that the velocity has to be Vs divided by epsilon. And it is on the basis of these length and velocity scales that you define the dimensionless group. Okay. In particular, the Reynolds number is equal to rho times V void times d void equivalent, okay, E by mu. Okay. And if you substitute these expressions for the velocity of the in the voids and the equivalent diameter of the voids, you will get rho V s d E by 1 minus epsilon times mu. Okay. That is the definition of the Reynolds number. Okay. And the friction factor is defined as delta P by L divided by rho V void whole square by d void. Okay. The kinetic energy per unit volume, okay, the kinetic energy per unit volume. Okay. Note that usually when we define a friction factor or drag coefficient, we take half rho v square. In the literature in packed beds, the half factor is not included. Okay. So, we write it without the factor of a half. So, this is equal to delta P by L times d void by rho v void whole square. Okay. And substituting the values that we already had, you will find that this is equal to delta P by L into epsilon cubed d by rho v superficial velocity square into 1 minus epsilon. Okay. So, this is the definition of the friction factor and the Reynolds number, okay, for the flow through a packed bed. Okay. And all these factors of epsilon in these definitions emerge because the velocity we have taken are the characteristic velocity through the voids, and the equivalent diameter is the equivalent diameter of the voids, not the particles. And if you relate the equivalent diameter of the void to the equivalent diameter of the particle, as I have done here, and the velocity through the voids with the superficial velocity, these are the definitions that we get. And the standard correlation that is used for packed beds is that the friction factor is equal to 150 by Re plus 1.75. Okay. This goes by the name of the Ergun correlation. Okay, this goes by the name of the Ergun correlation. Okay. At low Reynolds numbers, when the Reynolds number is small, right, the Reynolds number is small, this term becomes dominant. Friction factor goes as 1 over Reynolds number. Okay. When the friction factor goes as 1 over Reynolds number, the viscous effects are dominant, and the friction factor does not depend upon density anymore. Okay. It does not depend upon the density of the fluid anymore. Okay. So, this 150 by Re is the factor that you get at low Reynolds number, similar to 24 by Re for the drag coefficient, or 16 by Re for the flow through a pipe. Okay. In this case, you get 150 by Re. The difference between this and the flow through a pipe is that here the Reynolds number is defined based upon particle diameter, whereas in the pipe it was by the pipe diameter. Okay. And in the limit of high Reynolds numbers, this friction factor tends to a constant value. Okay. And this is the standard correlation that is used for the flow through a packed bed. Okay. So, let us look at an example of how we would use this correlation in order to determine the pressure drop for the flow through a packed bed. Okay. So, the problem is as follows. Okay. I have a packed bed. Okay. I have a packed bed. Okay. So, I will just rewrite it over here. Okay. You have a packed bed of length L, okay, and cross sectional area A, okay, across which you are applying a pressure drop. Okay. The particles, so the porosity of this packed bed is equal to 0.4. Okay. Okay. The density of the particles, okay, the density of the particles is equal to 1.2 into 10 power 3 kg per meter cubed. Okay. The density of the fluid is equal to 10 power 3 kg per meter cubed. Okay. And the viscosity is equal to 10 power minus 3 kg per meter per second. Okay. And the diameter of the particles is 1 centimeter, which is equal to 10 power minus 2 meters. Okay. And I want to find out what is the maximum superficial velocity. Okay, that can be used for running this packed bed. Okay. Now, see, the background of this is as follows. Okay. So, if you apply a pressure drop across, right, that means as the fluid is flowing through the packed bed, it is exerting a force on the particles. Okay. The force exerted on the particles has got to be equal to the difference in pressure times the total area, or the total cross sectional area of the packed bed. Okay. Okay. So, the difference in pressure times the total area of the packed bed, okay, will be equal to the weight of particles okay. It has to be equal to or less than the weight of the particles. If it becomes greater than the weight of the particles, the fluid will fluidize the particles and the particles will leave with the fluid. Okay. It has to be less than or equal to the weight of the particles, okay, for the bed to be stable. Okay. So, the question is, what is that limit? Okay. What is the maximum pressure drop that can be applied so that this limit is satisfied, and what is the superficial velocity for that? Okay. So, what is the weight of the particles? Okay. Okay. So, I should put in a caveat here. This should be the weight of particles minus the buoyancy force. Okay. Okay. Buoyancy force is the upward force due to the fluid displaced by the particles. So, delta P A has to be less than or equal to the weight of the particles minus the buoyancy force for the bed to be stable. Okay. So, the weight of particle minus buoyancy force will be equal to delta rho g, okay. Delta rho is the difference in density, okay, okay, into the total volume of the particles. Okay. The volume of the particles is equal to 1 minus the void fraction, okay. The total volume of the particles is equal to 1 minus the void fraction into the total volume of the bed, which is the area into L. Okay. The volume of the particles is 1 minus the volume fraction into the total volume of the column. Volume of the column is the cross sectional area times the length. Okay. Okay. So, at the condition at which the pressure difference times the cross sectional area is equal to the difference between the weight of particles and buoyancy force, you have delta P times A, okay, is equal to delta rho g into 1 minus epsilon into A into L. Okay. And the cross sectional area will cancel out on both sides, and I will get delta P by L is equal to delta rho g into 1 minus epsilon. Okay. So, this is the condition under which the weight of the particles is exactly equal to the applied force difference, okay, the pressure difference times the cross sectional area. Okay. And now I can use the Ergun correlation to substitute for the pressure difference per unit length. Okay. If you recall, the Ergun correlation is that the friction factor times the and the delta P by L is equal to the friction factor times rho v square into 1 minus epsilon by epsilon cubed times the diameter of the particles. In this case, the equivalent diameter and the diameter are the same because we assume these are spherical particles. Okay. Okay. Where rho in this case is now the density of the fluid. Okay. So, I should be specific here, I will write this as the density of the fluid. Okay. Okay. So, I get F into rho F Vs square into 1 minus epsilon by epsilon cubed dP is equal to delta rho g into 1 minus epsilon. Okay. Okay. And for the friction factor, I substitute the Ergun correlation. Okay. 150 by Re plus 1.75, okay, into Vs square into 1 minus epsilon by epsilon cubed dP is equal to, I will take the rho f to the right side, delta rho by rho f g into 1 minus epsilon. Okay. Okay, that is the relationship I get between the friction factor, substituting the Ergun correlation of the friction factor and the Reynolds number and the difference between the weight and the buoyancy force. Okay. So, for 150 by Re, I can write that as 150 mu by rho Vs Recall that the Reynolds number had this factor of, okay, of 1 minus epsilon in the denominator, okay, and the friction factor is the factor of epsilon cubed by 1 minus epsilon. Okay. So, substituting these, I will get 150 mu into 1 minus epsilon whole square, okay, Vs by rho dP square epsilon cubed plus 1.75 Vs square into 1 minus epsilon by epsilon cubed dP is equal to delta rho by rho f g into 1 minus epsilon. Okay. So, now I can use this, okay, substitute the values, okay, that delta rho is equal to 200 kg per meter cubed. Note that the density of the solid was 1200 and the density of the liquid was 1000. Okay. Epsilon is equal to 0.4, okay, and mu is equal to 10 power minus 3 and dP is equal to 0.01 centimeters per second. Okay. I should be careful here, mu is 10 power minus 3 kg per meter per second and dP is equal to 0.01 meters. Okay. I substitute that and g is equal to 10 meters per second square. Substitute all these numerical values into this formula and I will get a quadratic equation, okay, for the velocity, okay, because you can see that this first term contains velocity to the first power, the second term contains velocity square and the third term is independent of velocity. All other parameters in these equations I know and therefore, I can solve this. Okay. I can solve this equation to find out what is the velocity and I will get the velocity as 0.0246 meters per second, okay, or approximately 2.5 centimeters per second. That is the maximum velocity that you can use to flow fluid through this bed. If you go beyond that, the pressure difference across times the cross sectional area exceeds the weight of particles minus the buoyancy force, and therefore, the particles will get fluidized. Okay. So, that is the limit to the velocity that you can get and you can calculate a Reynolds number based upon this, which was rho Vs dP by 1 minus epsilon times mu, which is approximately 410. Okay. So, that is the maximum Reynolds number that you can use to flow the fluid through this bed. Okay. Okay. So, this is a simple discussion of the flow through a packed bed, the superficial velocity, the void velocity, the void characteristic diameter, which are both used for defining the Reynolds number and the friction factor. One of the simple correlations for this case, the Ergun correlation, and I have just given you an example of how that can be used to find out the maximum velocity at which fluid can be pumped through this packed bed. Okay. Okay. So, this is the discussion of the correlations for momentum transfer in a packed column. Okay. How do you define the friction factor, how do you define the Reynolds number, what is the correlation and how can that be used in a practical example for trying to estimate the pressure drop that is required for a specific flow rate. Okay. In this particular case, the pressure drop was defined by the maximum the condition that the weight is equal to the pressure difference times the cross sectional area. Okay. Next, we will go on to looking at some dimensional analysis for problems in mixing. Okay. I will continue this in the next lecture. I will see you then.